Hey there, welcome back. Um, this time I want to talk about quadric surfaces, which are another type of surface that you might run into. Basically, it's the simplest type of surface that involves only quadratic and linear terms in the equation, right? We could write, just like if we have two variables, you might have seen something like ax squared plus bxy plus cy squared plus dx plus ey plus f is equal to 0 when you were learning about conic sections. Well, after you had an equation like that, you simplified it down into only just a few different options of different things that can appear as a conic section in 2 dimensions. Well, now we're in 3 dimensions, and that means there's a whole many more terms to this expression, but the same type of setup works here in that if you do a rotation or a translation, there's really only 2 different classic forms of an equation that we need to think about and we need to consider. So let's zoom in and see what we can learn about these 2 different types of equations. The key aspect of these is you should work on recognizing them and understanding what's possible, and these are going to give us some new examples of functions that we can explore and do calculus on. Okay, so when you're trying to understand what's happening to these equations, then this is going to be similar to when we were talking about the contour plots from the surfaces. Here we're going to be taking slices, either parallel to the YZ plane, or parallel to the XZ plane, or parallel to the XY plane, taking slices. And by putting these slices together, we can recreate these 3-dimensional objects. All right, so let's look at this example. If we have something that looks like this, x squared plus y squared over 9 plus z squared over 4 is equal to 1, then we're going to make a slice. So let's first make a slices that are parallel to the xy plane. Well, things that are parallel to the xy plane are when we set z equal to be a constant. A simple constant is always 0. We like zeros. So we put z equal to be 0, and then we have an equation that looks like this. X squared plus y squared over 9 is equal to 1. Now, this is where we're going to bring back in some of the knowledge that, honestly, I have a hard time remembering as well. So we're going to bring this back into our short-term memory so we can use it and learn more about what's happening. So when z is equal to 0, we see this equation, and this feels a lot like x squared plus y squared equals 4, or is equal to 1, which we know is a circle. But in this case, we have x squared plus y squared over 9 is equal to 1. And so what that's saying is we've done a shift in the y direction. Instead of y, so up here, x squared plus y squared is equal to 1, I kind of look at that as saying, well, the x direction can extend from -1 to 1. So x can be between -1 and 1, and then x squared is less than or equal to 1. Similarly, y is between -1 and 1. And then that tells us that our circle is between -1 and 1, and -1 and 1, we actually do have a circle of radius 1. So in this picture, we have that instead of, so x still goes from -1 to 1, because when x is between -1 and 1, then x squared is less than or equal to 1. But now this y squared over 9 is telling us y could really go up to 3, or -3. We can have a picture here where this is -3, this is 3. And if y is in that range, then y squared over 9 is less than or equal to 1. So instead of a circle, this is going to give us an ellipse. This is going to give us an ellipse with, this is our x, this is our y. This is going to give our ellipse with, I think they're called semi-axes, semi-radii. I'm sure there's a better word for that. Of 1 for x and 3 for y. Okay, so that's what happens if we just look at what happens when z is equal to 0. So let me redraw this picture. So when z is equal to 0, that's this height, then it opens wide around the y direction and narrowly around the uh, x direction. Now, the thing that's different here than with the level curves, the contour plots that we did before, here we're choosing different z values, and then that's going to give us different slices in the x or y direction, parallel to the xy plane. We can also do this vertically, either parallel to the xz plane or the yz plane, and that's going to give us slices in the different directions. So before, when we were talking about level curves and contour curves, we really just have a function of one variable. We have z as a function of x and y. And so we can only take these slices that are horizontal. But in these cases, now we can take slices that are vertical as well. So this was one slice. This was when z is equal to 0. Let's say z is equal to 1. If z is equal to 1, the equation changes slightly. We get x squared plus y squared over 9 plus 1 over 4 is equal to 1, which means we have x squared plus y squared over 9 is equal to 3/4. So instead of being an ellipse where we have this x has distance 1, now x has distance √3 over 2. So what that's saying is that if we go up to height z is equal to 1, then we have an ellipse that's a bit smaller. And then if we go up to z is equal to 2, so if we plug in z equals 2, we get x squared plus y squared over 9 is equal to 0. And so we're at this point. So if we also do z is equal to 1 and z is equal to 2, so z is equal to -2 and z is equal to -1, then we start to see that we have this, it's not quite a sphere, it's kind of ellipsy of a sphere. So this is actually called an ellipsoid. All right. Let's do another example here with a slightly different type of function. Here we have z is equal to y squared minus x squared. And for this example, let's take slices in each of the different directions. Right? So if we have something that looks like x is equal to k, remember that is in the yz plane. That's parallel to the yz plane. Y equals k is parallel to the xz plane. And z equals k is parallel to the xy plane. So if we substitute x is equal to k here, we get z is equal to y squared minus k squared. And so as a conic section, we get z is equal to y squared minus something, minus a constant. And so what conic section is that? Something that looks like y is equal to x squared. That's a parabola. Okay, and what do the sketches of that look like? So we're in the YZ plane, and so we get things that look up, and then as we move out in the K direction, the slices end up moving down. And then if we move in the X direction, so then these ones are in the back, these also move down. So it's kind of like a parabola that goes up and waving down. All right, but let's get some additional data, and let us use that to help our drawing. All right, so z is equal to k squared minus x squared. So what is a function that looks like y is equal to negative x squared? Oh, you know what that is? That's also a parabola, but they're opening down. Okay, so parabola opening down. So if we go in the zx plane, then we get this parabola opening down. But as we get further away from x equals 0, or k equals 0, I guess that's y equals 0, then our parabolas go higher because k squared is positive. So when k is equal to 0, we just get the function, let me make that one black. When k is equal to 0, we get z is equal to negative x squared. Whereas here, when k is equal to 0, we get z is equal to y squared. All right, last is this xy plane. And for the xy plane, what we have is k is equal to y squared minus x squared. So what's that conic section? Something that looks like x squared equals x squared plus k is equal to y squared, or y squared minus x squared. That's a hyperbola. Okay, that's been a while, right? Okay, so what that's saying is that those shapes look like this or like that. So when k is equal to 0, we have x squared equals y squared, and that's actually a degenerate hyperbola, where you just have an x. And then when you go up, you get hyperbolas that look like this. When you go down, you get hyperbolas that look like that. Okay, this is impossible to draw. That's why we will like to use Mathematica. But we can, it's actually not too awful to assemble these two pictures together. So let's create our 3D drawing. We have z is equal to y squared, and we have our picture that z is equal to negative x squared. And so what we get here is that these end up going down on both sides, and then these go up. Alright, I said this wasn't impossible, but it's still not pretty. If you look carefully, you might see a surface that you're used to seeing on a Pringles, on a Pringle from Pringles potato chips. So this type of object is called a hyperbolic paraboloid. And we'll take a look at that shape in a second. All right, so here's the takeaway message. There's 6 different families of quadric surfaces. So we can talk about ellipsoids. Ellipsoids are these functions that that look like spheres but stretched in some direction. And the way you can tell these different families apart is by looking at what the coefficients are of these terms. So there's these 4 different examples. When you have something that looks like x squared, y squared, and z squared all involved in the equation. If the coefficient are all positive, then you have an ellipsoid. If 2 of them are positive and 1 is negative, then you get something called a hyperboloid of one sheet, which kind of looks like that. We'll see a picture in a second. When you have 2 of them are negative and 1 of them is positive, then what you get is something looking like a hyperboloid of 2 sheets. And what we've done here is we've written these as x squared, y squared, and z squared on one side of the equation, and a positive number on the right side of the equation. If that number is 0, then what you get is a cone. Right? This is just kind of like the degenerate case that we were talking about with the hyperbola. You get an x, here we get a cone. You can kind of see the x in the cone. So that's what happens when you have the x squared, y squared, and z squared all in the same equation. If, on the other hand, you have a z on one side of the equation and an x squared and a y squared on the other side of the equation, you either have something called an elliptic paraboloid, or you have this shape that we were talking about earlier, which is this hyperbolic paraboloid, and which is kind of impossible to draw. So we'll draw a picture in a short time, but the key idea that you need to be able to do are matching equations to surfaces, and understand that these are the higher dimension versions of the conic sections. And be able to substitute and plug in y equals k into this equation, x equals k into these equations, z equals k into these equations, and look at what the slices would look like in order to figure out a rough sketch. All right, let's head over to Mathematica. Oops. So for Mathematica, in the Mathematica file that you see, you can play around with the different options. So for example, here we can change these axes, and if you have something a squared plus b squared plus c squared is equal to 1, then you get this shape that's either a sphere or some ellipsoid. Ooh, look, a skinny ellipsoid. Donut. All right, but if one of these coefficients becomes negative, then it looks like then what you get is this shape that is the hyperboloid of one sheet. Let me make this a little bit bigger, and then you get this, I mean, it's an interesting funnel-like shape. If 2 of them are negative, then you don't get a funnel, you get this double object. Let me make these 2. Here's what I really want to do. Make this one like this. So you get this shape that has, it's interesting because it's disconnected. It's not a connected shape. And you can see here we have, it's a disconnected surface. So here we have 2 negative signs and 1 positive sign. So for all the different values there, you get this hyperboloid of 2 sheets. And if all 3 are negative, well, this equation is not possible, because x squared is positive, y squared is positive, z squared is positive, so you can't have a whole bunch of negative values be equal to 1. The cone is what happens when you have 2 of the coefficients positive and 1 of them is negative. So you can either have a cone that direction, or that direction, extending out. And then the last family are these paraboloids. So you can, if both of the coefficients are positive, you get this bowl-like shape, which is elliptic paraboloid, right? This is an ellipse. But if we get this negative, then we get this potato chip-like shape. This is called a saddle. And this will be an interesting thing to do calculus on in a short while. So as we change these parameters, we get different shapes. This one's really potato chippy. All right, let's stop there. Now we've seen a whole bunch of surfaces. The next step will be to do some calculus on them. All right, see you later.